I like this opportunity to talk about Opticlock because over the past years, this has been one of my favorite projects, and maybe I can transfer why that was the case. So yesterday I talked about cooperation. I think, in my view, it's a wonderful example of how cooperation can really be efficient and be also enjoyable for everybody. So you see quite a few authors here, and I should say the first author, Niklas Huntemann from the PTB, he is the one who prepared most of the slides. So I have to be thankful for him first. And then you see my name, of course, because I will now be speaking. And there's also Stefan Bracane, who did his PhD with me. And I think one of the best routes to transfer knowledge is to have somebody taking his knowledge from an academic lab all the way into an industry lab. And exactly this happened. He started working on this project with our lab and then and then took the future route to Toptica. So let me start immediately. This topic is maybe not at the center of quantum networks, although in the long run, I think we will need very good frequency stability and very good timing systems. And for good timing, we need optical clocks. And my personal view is also that if you want to be successful in the big promises of quantum technology and quantum computing and so on, you must be willing to go for clock physics, which is the ultimate way to do precision physics. Okay, so this is a special one. It's a ytterbium single ion clock. I will give you a few overviews why it's useful, and then I will tell you about where we are. And as I said in the title, it's almost ready for rollout. And so why would we use optical clocks? And why would we like to use them? So one is satellite navigation. You all know the GPS or GLONASS or whatever system. And so new versions of that would even improve the stability and the precision. And this is one of the applications. Then synchronization of large networks. So telecom, VLBI would be for astronomy also. That's something which we need to be better. Timescales. As far as I understand, Industry 4.0 needs better timing than we have at the moment if we want it to become reality at the microsecond level, and we need better atomic clocks for this. A very interesting application is relativistic geodesy. For instance, we are already now trying to observe what happens with the ice shield on Greenland via measuring the gravitational effects, and the new clocks put onto satellites could be precisely enough, or could be sensitive enough to see the variations of the ice shield on much shorter timescales than we do today. Today, we need to average for a very long time to see differences, and we would like to see this more or less in real time. I have to say, from this situation, we have clocks on the ground which are at this level, which you need at the level of 10 to the minus 18 or maybe even 19. But in space, this is, I think, a couple of years ahead. So, but on the lower right, what you see, this is an experiment where it was shown that the relativistic variance, when you go from a higher altitude to a lower altitude, can really be measured by just measuring the clocks. You see that in these two plots here inside. Okay, so I think there's good reasons beyond having the drive in physics to go for atomic clocks to improve them also for applications. Now, what do we have today? This is microwave clocks. This goes back now roughly 70 years, 65 years or so. No, 75 years. No, not quite, sorry. 1955, the first ones were put into operation at the NPL in London. And so these are towers like this, and they are towers like this because they are fountain clocks. Yeah. So let me actually change to my laser pointer. So what you see here, so there are atoms thrown up and then coming back down, and during the time they went up, they oscillate, and it's the oscillation that is measured to without any disturbance, roughly speaking, and this is what is defining our time scale. And so more in physics, we have then two atomic levels, and the atomic clock runs at 9 gigahertz, and the future optical clocks run as you see, 10 to the 5 times, roughly 10 to the 5 times higher frequencies. And why are they more precise? In simple terms, it's very easy. You have simply more oscillations per second, and so you can simply count more oscillations, and that's why optical clocks are favorable. Of course, you need to do a hell of a lot of things in terms of precision analysis and so on. I don't want to go into the details of that. So let me switch on. So what happens in reality is you need a laser oscillator. This is just the instrument. It's a cavity stabilizing. This laser is a flywheel. And this flywheel runs all by itself and needs to be stabilized to the atomic reference. And then you need a detector in the feedback system. And once you have that, then you can, for instance, use a frequency comm generator. And in 2005, Jan Hall and Tiet Hensch received the Nobel Prize for this, which I think is a true revolution in this technology. So optical clocks, here is also something very interesting. I did my PhD around 1980, beginning in 80, quite some time ago now. And as you see, I remember very well. So you could buy commercial atomic clocks at the level of 10 to the minus 11 from Hewlett-Packard and others or so. And the best atomic clocks were at the level in the lab were at the level of 10 to the minus 13, maybe 14, and so on. And this is all these continuous evolution of the basically the cesium atomic clocks. Why cesium? Simply the reason why they use cesium is simply because cesium is a heavy atom, so it moves slowly. And if you don't have any trap or so, then this is the atom to go for in a slowly moving and therefore for a long time observable atom. And then around this time already, there was optical clocks coming onto the screen. So you see here some first examples, which actually is the ytterbium clocks already. And they have come down in stability and precision enormously, as you see. Yeah. And so as you see, they have crossed the line of the microwave clocks. And now this will be the future standard. And I think we are going to switch to optical clocks, also probably in the definition of the SI second at some time soon. So why ytterbium? This is a level scheme. I don't want to take you to the details or so. You all know we are representing energy levels in atoms with these bars or so. The details are really not important. And a typical resonance line makes photons scatter very often between the two levels. And that's not good for a true atomic clock transition. For that, you want to have something slow, which is almost forbidden. And that's what this E2 and E3 means here. And historically, I find this quite interesting because around 1980, I think Rainer Blatt was traveling through our lab or so, and they had just found this transition or so. And we all found this very fancy. And so in hindsight, I find it absolutely amazing that nowadays we really build some of the best optical clocks on this transition. Yeah. And actually the clock transition that we used for the one to be rolled out here is this E2 transition with the number behind it. So it's an electrical dipole transition. This is an octopole transition, a quadrupole transition. This is an octopole transition. Basically, the intensity goes down by alpha squared. And so that's why you simply have more signal on this transition than on this one. And so at least for the first instance, I think this was the better way. So how to characterize an optical clock, that's shown here. So you always see these plots. This is the fractional frequency stability. You see here the numbers which are of interest. So 10 to the minus 15 at 1 second would be here, the uncertainty or so. And then you just see these lines, or also maybe a plot of measurements going down here. It roughly always looks like this. And why is that the case? What can we understand from these plots? Well, in this part, it's simply a realization, if you want to, of the central limit theorem. If you do more measurements, you can determine the central value more precisely. That's very well known. Yeah. And so what we do, it's a running average, and the longer we average, then the narrower gets the number. However, at very long times, then this distribution starts to wander off and starts to drift away because there are systematic or environmental effects which we do not control. And so you always see this turnover, and we want to, of course, keep it going in this direction as long as possible. You can also translate this into rather than the frequency instability into a time instability. I think this is more directly and more easy to understand. So here we have, this is roughly 1 hour, the stability at 1 hour. So here we would have for the microwave clock, typically 10 to the minus 15. And then we would go on. And by the way, there's an interesting aspect here. Here you see the hydrogen maser, which has been around since the 1950s also. And it's even better than our atomic clocks. However, as you see here, it drifts a lot more. This is, for instance, due to the coverage of the internal surfaces of the microwave resonance cavity with unwanted materials or so. Okay, so this is as I said it, so you see these, and actually in a measurement, you know that the average value also of the average value goes down by square root of the number of measurements you can take, and since the number of measurements is proportional to the time, it simply goes down by the number of to the -1/2. Okay, also, so we see here that there is this turnover point again, and this is the aim of the Opticlock project, which we started. All right, so let me go on. Yeah, so we started this project in 2016. The idea came around in 2016. In 2016, there was a convention at the BMBF, and the decision was, well, it looks like Germany should do something about quantum technology also. The UK had already started to invest money, and other countries also. And so then what can we do in a very rapid time? And I think Gerd Leux from Erlangen deserves a lot of credit for taking the lead in this. He created this program, which was initially called QTEGA, and then an amazing, even in hindsight, I think an absolutely amazing procedure took place. Remember, I think in July or so of 2016, we all met with, I don't know, some 20 or 30 people, and we said, okay, the recommendation was bring out a general call for anything you would like to do in quantum technology as soon as possible. So the deadline after the call was in November, so there was about 4 weeks to create concepts or proposals. And then Gerd Leux, and initially I didn't believe it would work, but he said, okay, we just take the community and we just cast a vote on this. And so after all the proposals had come in, then the community, you had to fulfill certain qualifications, was supposed to vote on it. And there was about 60 or 70 voters or so. And on the left side, you see the result. Yeah. And so within 1 week, we had some kind of result. There was a final decision-making workshop on November 30. And as you see, of course, if you are one of the winners, there were 3 winners, then it's clear that you rejoice about this. But I think the procedure in itself is highly interesting because it showed that science can be very efficient by deciding on what should be funded and so on. And then no later from this, then in January 17, the Opticlock project started. Now there was one really very lucky circumstance, that is, as you see here, this is the total number of votes voting for these 3 top or front-running projects, and there was a clear gap for the next one. And so I think this made it relatively easy and acceptable for the community at large to say, okay, this is the decision for the projects that we want to fund. But I think there's a lesson which at the very present time, I think we should try to put forward into the decision-making ranks again. That is, science is able to take very reasonable decisions, even if it's not to please everybody or so. All right, so now let's go to our project. So as we say here, it was one of the 3 pilot projects for quantum technology in Germany. And so this is I will say a few more words about this. And so it was for 3 years. And the idea was to develop a robust, high availability, easy to use optical clock, which could be rolled out, yeah, and taken out of the lab. And so in the end, what happened was this consortium consisted of 6 companies. We will see a few more of these in just a moment. 2 universities, one of them I'm from the University of Bonn, a research institute, and also a federal institute, which is the Physikalisch-Technische Bundesanstalt. We had project coordination from industry, Jürgen Stuhler of Toptica, and Pete Schmidt of the PTB in Braunschweig, which is the federal institute, were taking the scientific lead. And so here's the consortium again, and you see a little bit what the highlights were. So there was miniaturized diode laser sources by the Ferdinand Braun Institute. There was vacuum, which you need. Toptica builds lasers. Cubic builds modulators. High finesse measures all the wavelengths. Quartic provides the software which is necessary. PTB really had the model available, and so was taking the one part of the integration service together together with Toptica. Universität Siegen, Christoph Wunderlich was going for the next stage already to bring it even beyond the present system. Menlo Systems was doing the frequency conversion measurement again. And our role was, as you will see in a moment, to work on the optical and the physics package in this. So again, what's an optical clock like that we want to roll out? There is some physics package, as you see here. So it's basically an ion trap as we do operate it and like it in our labs or so, yeah? So it looks here with wires and fields and so on. All that is clear. You need lots of lasers. In our case, I think it's 4 lasers, and they need to have extremely high stability. They need to be push button operated, and they need to be available at all times, yeah? And so, of course, you need a lot of control electronics. And then there is, as I said earlier, the atomic clocks always consist of something which nature gives us, like a single ion from the terbium period table or so, and a flywheel laser, which you stabilize this and which can then be used to distribute the frequency and the time that you want to have. Okay, so this is as simple as it is. And in a sense, what we have in our labs needs to be put on a dollhouse situation. So this was the aim. Yeah, and this is actually what it now looks today. And so this was the aim, have 2 racks available for this optical clock, which you can, it's on wheels, so you can literally roll it out or so. So here's the laser head, there is the control system, there's the measuring the wavelengths. This is the physics package. This is where we and the universities were involved, as you see. Again, there is the lasers and so on, and the control hardware. Okay, so that's how we did. And as you also see, everybody had his specific task in all this. And okay, let's go on. That's not so important in this case. So this is the physics package. And again, on the left side, it looks a little bit like it still looks in our labs. Yeah, it's perhaps more carefully designed and compactified and so on. But basically, it's the way we know it from our laboratories. And so, yeah, I don't want to go into all the details here. So it's resonators, cameras, ovens, and so on, whatever you need. And yeah, this is the ion trap, and maybe I skip over yeah, basically, so for the experts, maybe this is about Ramsey spectroscopy in the optical domain. If you know what Ramsey spectroscopy is, it's fine. Then you can, I think, cherish this kind of a clean signal that we have here at the time scale of milliseconds, which is what you need to achieve this ability. If you don't, if you're not familiar with Ramsey spectroscopy, then just forget this slide or so. We'll just skip over it. And let me come to our contribution or so in this. Yeah?
We are now in the Q&A part, time-wise.
Pardon?
We are now in the Q&A part of your talk, time-wise, because it's 20 minutes plus 10 for the questions.
I know, but I also started 7 minutes late.
7? Okay.
Yeah.
So.
Okay.
Yeah, sure. Then go on.
Okay. Okay, then I will try to be very rapid. So our expertise you can ask me later on, to build a really high quality numerical aperture objective. And we did this very carefully, and this is what we have done. And here you see that it's really able to see single atoms. And oops, now my thing starts here pushing by itself. And so again, this is the physics package. And here's the single ion that we wanted to observe, and where we had the expertise to build professional optics for this purpose. All right, so let me skip in the interest of time also over this here. And so here, this is now the operating system, and the most important thing here is what you see on the top, the red line. It's availability over 14 days when it was measured with unattended operation was 99.8%. This is what you want for something to be in easy use and for straightforward and continuous use. And so this is now Opticlock. You see it on the left side here, the yellow box actually is Opticlock. It's these 2 racks. That's what you can see. And it's not the Hall of Fame, but maybe the kind of the Hall of Fame of the clocks at the PTB in Braunschweig. The most famous one used to be the Cesium clocks here. And you see there's more ytterbium clocks. And so the good thing is you can compare all these clocks with each other, because otherwise you have no chance to take any note about their stability, yeah? And this is the final evaluation of our clock. So this black line here, this is now what you see. This is the Opticlock, yeah? And you see it's better than the hydrogen maser. And in fact, the market Opticlock is aiming for is to replace hydrogen masers. I think there are 500 or more hydrogen masers in the world, and they should be replaced. And you also see that an even better clock is this Terbium-2, but this is under laboratory conditions only. Now, this is this 2-rack, really compactified system, and it lives absolutely up to specifications. So it does have this at 1 second, then, so to say, the 10 to the minus 15 number here, which is a new area and a new regime for optical clocks. Okay, let me come to the end, more or less. Now, what I really enjoyed about this, it was a team effort. And it was not this kind of a team effort. So yes, this is one method to organize perhaps cooperation, that there's lots of bosses and then a few have to row or so. But I think maybe even you can see this. I think the mood was just excellent, superb. And everybody was really ready to do his job and not to be only interested in the highlights that you get. Yeah, and so because it's necessary that you do perhaps very boring things, and only then I think you can be heading for a success like this. And I think you see it in the smiling faces here or so. And I think that's my last slide. So Opticlock, I think, is a very nice example for user-friendly quantum technology to be marketed now. It's fully automated. The performance is evaluated. It lives up to the expectations. And there's also availability of subsystem. There are spin-offs now, which are now used in these labs. So there's multi-laser sources with digital frequency control. We have new compact lasers. There's resonant microwave electro-optic modulators, and especially the control hardware and software at PTB is now wandering to many more labs. And perhaps I would like to also stop with this. For my point of view, for this talk, also the three most relevant people is Pete Schmidt, who is the scientific organizer, Jürgen Stuhler from Toptica, who is the commercial organizer, and my former student, Stefan Bracane, who started out as a PhD student on this, took his knowledge, is now working for Toptica, and went, I think, the optimal route for knowledge transfer from the academic world to the industry. Thank you very much.